So we can get started. Good afternoon. So you must have seen the next homework assignment, right? And I like the way most of you wrote the first report. I think that sort of a thing it's fine. So this time I would like for you to kind of investigate what the WebEx system that Notre Dame has to see how that sort of works out, right? Some of you went really beyond what I had expected for the report for the first one. It's good. I mean, I'm not going to say don't do that, but I think I gave extra points if you went over beyond what was expected, right? And I think one of the things that you realize is depending on what you chose, you come up with big numbers, right? Millions and so on and so forth. And some of you didn't know what's the realistic number for these kind of systems. And one of the reasons why I sort of don't like the Google model is Google kind of hides all this cost from you, so you never quite realize what you get because the cost, you don't pay the cost, the advertisers pay for you kind of stuff. Some of you mentioned that they found that to run YouTube for a year, for a month, they cost $90,000. I didn't follow. I think you had it, right? Yeah. YouTube for a month cost $90,000, right? What is this? What was this about? Is that how much it costs them?
No, it's 90,000 a day.
A day?
Yes.
So it's 90,000 a day for what?
Like the service costs.
Okay, for the entire service, or?
Yeah.
Okay.
YouTube has to pay that much a day on an average.
Okay.
For whatever you do.
Okay. I mean, the cost is kind of pretty bizarre, right? So many of you realize that depending on what you're asking for, the cost changes, right? Many of you wanted large server, and some of you went with a small server within the Amazon model. I'm not particularly sure that you need a large model because depending on what you're trying to do, you're just trying to serve contents which is stored somewhere. So you may be okay with the small, but you see the cost variation, right? And actually, I think Amazon is pretty cheap as things go, right? You can't beat Google, but that's because Google starts with infinite money. So anything added to infinity kind of still remains infinite, right? So anyway, so that's sort of the thing. And if you have to do it yourself, things add up very, very quickly, right? And you don't quite realize it if you're doing this from Notre Dame because somebody else pays for the internet connection, somebody else pays for all the stuff. But once you add those things add up, right? So anyways, the next topic I would like to introduce is the notion of video sensing or sensing in general. It's very important because it's a lot of people are excited about sensing, right? And one of the reasons is the hardware has finally caught up to a point where you can extend your computing out in the real world, not just on video, but on other stuff. So I can build these small, inexpensive kind of stuff, where inexpensive depends on what you're trying to do, right? So if you're talking about infrared, $50,000 is inexpensive because a few years back, it used to be a lot more than that. But you build lots of these things, and you can put them out in the real world to sort of see what's going on. And you have the networking and the computing capabilities to sort of monitor the whole world, right? And people are excited about this because now you can see and do stuff that was never possible before. And I found some, and of course, most of these technologies are driven by military, so they want to have, deploy this on the battlefield, be able to hear when the tank moves, and so on and so forth. But the other interesting aspect is monitoring environments, right? One of the problems with the military stuff is their budgets are similar to Google's budget. So they do different stuff than what the environment folks can do because environment folks tend to be researchers, quite frugal, so kind of stuff, right? So I'll show you two videos of what this sort of a technology can bring to the world. So essentially what it brings is, before I had these capabilities, if I want to monitor something which is extremely slow in happening, it's extremely boring, right? There was only one alternative. The alternative was to send a graduate student, right? Send a graduate student out in the world, out in the field, and let them sit there and watch these things happen slowly, right? So if you're watching, I'm not joking, right? So if you're watching, so one of the things that they want to do is watch when the high tide comes in and when the high tide goes out, because everybody knows the high tide, you see the end result. You see the water kind of come up, but you don't quite know how exactly the water kind of goes up and how it comes back, right? And apparently this shows where the sandbanks are, and apparently this shows what happens if you add pollution, all those things. So if you're by the ocean, you want to study this stuff, and you really want to study them not on a local phenomena, but across the whole thing. So one of the studies they wanted to do was monitor the whole of Oregon coast. I think watch something every quarter mile. So I think it turned out to like 1,300 video sensor, right? Or 1,300 graduate students. So you send them, you sit there, and you sort of watch the high tide kind of go up. If you watch high tide go up, it's not exactly, things go up and come. Like over a few hours, it kind of sort of goes up a little bit, and then it goes down. And then you sort of do this every day till you come up with a model of what really happens, right? Turns out graduate students don't really like doing this sort of a thing. So you want to have something with the sensing to do this kind of stuff, and that's one of the projects that we'll look into, right? I doubt it's doing.
The system software is going to need to be flexible enough that you can put it anywhere.
Stop. Something is supposed to happen, but okay, so this is one of the stuff from the Woods Foundation. They talk about what the stuff that the scientists want to know, right? All the biology stuff.
About a week to make a transect across the shelf break. Multiple gliders will allow large-scale ocean features to be mapped. The backbone of the observatory will be an array of moorings and surface buoys spaced out over about 40 kilometers across the shelf break. A variety of moored sensors will continuously sample the waters across the shelf break.
This is what they want to do, right?
Giving scientists a view of how conditions change vertically, horizontally, and in time. Powered autonomous vehicles
trying to build these things which are supposed to go
around the moorings, resolving small-scale features. Docking stations connected to the moorings will allow underwater vehicles to transfer data and recharge their batteries. Two-way communication via satellite will allow researchers on shore to monitor ocean conditions in real time, and will also provide the capability to reprogram instruments and vehicles in the array. With two-way communication and control, researchers can adapt and adjust their sampling plans as natural conditions and events dictate. This combination of pioneer array observing elements will provide an unprecedented view of the ocean in both space and time.
So this is like 1% vision of what they want to monitor, right? So these scientists want to sort of deploy these things, things going up and down and charging and all those things, but essentially trying to look at phenomena which happens over a long period of time over vast regions, and you want to sort of monitor what's happening, right? So I don't know how many of you watched the NOAA program on PBS, like I think a week or so back, right? They were showing the one of the projects from using the extreme ice survey. Did anyone watch this stuff? Right? So this particular program was pretty interesting. So what they were trying to do was they're watching glaciers melt, right? And you suspect that they don't melt fast enough for you to see, but it turns out they actually melt fast enough for something to be observed. So what they want to do is they want to deploy all these cameras sitting there and leave it on, right? And they kind of taking pictures of the glacier every hour in their case. So every hour during the daylight hours, and it keeps capturing those pictures. And then you kind of want to have a video out of these things to see what is essentially happening, right? So once you do this, things which don't appear to be happening on our life, I mean, we don't expect the ice to be able to see the ice melting, but once you kind of do it over a period of time, you see these things happen. And they're deploying this throughout the planet from different locations. And if you get a chance, you should try to look at that NOAA program. It's sort of interesting, right? I have no idea why the network is so slow. So anyway, so the idea is to monitor these things, and they set it up to capture every 1 hour. And if you watch the program, one of the events that they want to watch is on top of the. So there's a huge chunk of ice, right, on Greenland, and the ice melts and forms a little lake, right? And every so often, the water vanishes, right? So all they knew was the water sort of vanishes. They didn't know what happens to the water, right? So they had all these cameras looking at these things, and essentially a big lake drains out within an hour. So you need something much more higher fidelity than what they were trying to do, because if you're doing once every hour, you don't watch. So in the last shot, you see this lake fully full. The next one, it's completely gone, and you can't really see. So it turns out, I think they believe that the water goes all the way down and does something. So you want to be able to watch these things much more finer granularity than what they're trying to do. 1 hour is good for some things. It's not good for something else. 1 hour is good for seeing how the stuff goes back. 1 hour is good for downloading this page, but it was not this slow. I'm going to let it down for a little bit. So watching the glacier retreat over a few years, 1 hour is good enough. But if you want to watch something like this, when the whole sort of lake goes away in an hour, you want to have the facility to be able to monitor them much more constantly. And since you don't know which one is going to drain out, you want to be able to monitor a whole bunch of lakes to figure out maybe you'll get lucky. And so you want to have lots of these sensors monitoring these things and collecting these things, and be able to program them is what you want. I don't know, I think something is wrong here. Yes, this is what one of the cameras was watching, right? So that's the glacier field.
This is the Columbia Glacier in Alaska, and it's retreated over 11 miles since the mid-1980s. And here you can see where it was in June, then in May, then in October of 2007, and then we begin our time lapse, and you can see the glacier flowing in from the right. At the same time, the terminus is retreating, pulling back up the valley. And even in the wintertime, the glacier is for the most part retreating. Then it eventually catches up to itself, starts to advance for the summer. And you know, when you really have to look at this 10 or 15 times and watch all the amazing little details. These crevasses form on the right side, and all of a sudden a huge ice island will break off. But then by the time we got to June, the glacier had retreated so far it was almost back out of the frame again. So we pivoted the camera and then turned it back on and watched it rolling down the valley again. This glacier is, I would bet the cost of my daughter's college education on the fact that this glacier will retreat out of this frame within a year and a half maximum. And over the next 10 to 15 years, it will retreat another 5 or 6 miles up to the right before it finally gets grounded back on land and stops retreating. And so eventually at the end of this, we pull back so you can see the cycle of what's happened just in the past few years at the Columbia Glacier. The total retreat in the few years is 1.25 miles, and the retreat in that period is.
Okay, so I mean, the scientists are talking about what this means for their own research, right? But from our perspective, it's what we can do for them, right? Being able to watch this stuff. I'm not sure there are too many graduate students who want to sit on top of the ledge through the winter at minus 40 degrees centigrade or something, taking pictures every so often. And being able to collect these things is a very, very important contribution to the community, right? There's more information at that website if it were to download. So they're trying to collect a picture every hour. So in this case, they actually used a digital SLR. So I think it's 10 megapixel camera. So it was capturing fairly high quality image, not a video, and it's taking snapshots of pictures and stored on the stuff. And I think it gets very windy up there, and it's very cold. So it goes to minus 40, cold, and 160 miles per hour wind and everything. So it has to sit there, and they have to mount this stuff. So each camera, the whole mounting gear takes about 70 pounds. So if you go to the web page, you can actually see how they have to move this thing, because you essentially set them up way up there so you can watch over the whole year. And they collect data out of this in the old-fashioned way. Essentially, you fly over, you pry open the thing and take the video card out of it. So there's no networking involved with this particular stuff, right? And that works in this particular case because there are not that many cameras. They set a few of these things. But once you imagine going beyond the few, and then you have lots of them. So in the case of the Oregon stuff that I was talking about, if you're having 1,200 of these cameras, having somebody go in there and collecting the video card out of them would be a full-time job for a few people, right? So I don't think we want to create jobs like that. So you want to be able to collect the images using more networking technologies. And okay, so just asking for.
It was like watching a gigantic ship sink, and suddenly, right before our eyes, the thing broke off, flipped over, and drifted out into the ocean.
Rock?
Yeah, so
everything we're trying is getting thwarted.
It's all about the electronics not wanting to work.
Oh, happy day. It's all there.
In the Extreme Ice Survey, we're making a unique record of a unique moment in geologic time.
We've gone to a lot of amazing wild places: Greenland, Iceland, the Alps, the Rockies, British Columbia, and Alaska. We've stationed 26 cameras at 15 different glaciers. These cameras shoot one frame every hour on the hour as long as it's daylight for over 2 years. In the end, we'll have an extraordinary record of the world in flux. That landscape is gone. It may never be seen again in the history of civilization, and it's stored right here.
Definitely one of the strong points of the EIS is that they're looking at glaciers all over the world. And that means that you're not looking at an isolated phenomena, you're looking at something that's global in its pattern. And so for that reason, I think that seeing the kinds of changes in glaciers that the EIS cameras will record is going to show that it isn't something unique to one place.
I think we're living in an incredibly decisive moment of historic geologic time. And I think it's an amazing opportunity to see epic things happening right in front of our eyes. These cameras will record that for us.
I can't wait to see those cameras. It's been 10 weeks since they were put out, and in the meantime, the Mendenhall's had the biggest cycle of calving that anybody's ever seen here in 45 years. So we should have amazing results on those cameras.
Oh, fantastic.
We have 1,577 frames. It's been working the entire time. It's a beautiful thing.
This is it, ground zero. More ice is released into the global ocean from this glacier than any other glacier in the northern hemisphere. If sea level rises, this is where it all begins. This is it, ground zero.
Hey, I think you get the picture, right? So the links are off of the presentation, so you can take a look at that. So this is a project which is right now from Portland State. That's the one that we will look into in the class. So I'm going to let the author give a talk. He was giving a talk at a conference.
As you get to these types of mixtures, the interactions are going to be very specific to the plane. So what this really implies is that eventually the system software is going to be need to be flexible enough that you can sort of put it anywhere and sort of deploy it quickly. One other quick example is this whole environmental monitoring thing. So the guys at the Oregon State University have a video camera hanging out of a lighthouse, and they're sort of looking at the shore. And I came across this and I'm like, that's kind of peculiar. Why are they doing that? Well, it turns out they can do pretty wacky things. So they draw these diagrams of the shore over here, and then they basically stretch out the image. And then using image processing techniques, they can do crazy things. Like they can tell you how far offshore, how far underwater the various sandbars are underneath, and how they develop over time. And part of this is they're trying to understand the microorganisms in the water and how these sort of macroscopic things affect the smaller areas. So this is another example, and in talking with these guys, we showed them our video sensor stuff, and they were absolutely thrilled. They were like, "Where can we buy these things?" We were like, wait 20 years or whatever the current. So we said, "Well, how many do you want?" And they're like, "Well, to start out at a minimum, one video sensor every quarter mile along the Oregon coast." I guess they're not interested in California or Washington. But anyway, so if you look at the map, it's roughly like 300 miles. So you put one every quarter mile, you're at like 1,200 sensors. And you're like, wow, that's crazy. And then you get this thing. If you've ever been out to the Oregon coast, there are parts of the coast that are just really, really harsh. So you go up, there's a cliff, just goes down, and you see the water, down below. And, there are places where you won't see power in a long time. So that means you've got to build this system to deal with sort of long-term self-autonomous.
So I'm going to stop this one. Again, you can watch this offline, right? So that gives you a flavor for what people want to do. And I think another project people are looking at was along the Red Sea, the oil pipelines. They want to monitor these things for vandalism, right? So over a few thousand miles, you have these oil pipelines. You want to take a big camera to watch these things, right? And turns out for most of the time, nothing really happens, right? I mean, these are remote locations that you see the big pipe, nothing really happens, except for that moment somebody come and try to sabotage it, either blow it up or what have you, right? So you want a system where it's, 365 days, nothing happens, except for the 5 minutes something happens. So you want to continuously monitor these things, and you want lots of these, and how do you do that, right? And one of the things we realized from the little experiments we were doing with streaming video and stuff, right? So we had one camera and trying to stream it from my camera here to one of your laptop or something. You notice how kind of problems with the networking and stuff like that, right? Now you want to deploy this out in the field, right? So what are the different problems that you run into when you want to design thing like that? Taking the stuff that we talked about, right? So we need some sort of a camera, right? And we need some sort of a networking, because like I said, I don't want to go and take the video card out of all these things. And we need some kind of a CPU, right? And we need some kind of a battery to power these things, right? Without looking at those screens, right? Because they made one specific design choice, right? So what sort of a camera would you want to deploy for these stuff, right? What sort of camera, meaning what sort of a video resolutions, and all those things that we talked about, what would you like to give for something you can think of, right? Let's say you want to monitor the ocean stuff, right? What sort of a camera do you think you would want here? Yeah?
Well, if they're doing all that image processing now, you call on pretty high resolutions, you can capture the details for analysis.
Yeah, you would want as high resolution as possible, right? But the annoying part with the sensors is you also need the optics to go with it, right? So you can't, sensors are no good if you don't have the optics, right? So you need to have, if you have enough optics, right, then you want pretty high resolution stuff here, right? And if you have high resolution here, then you sort of need high resolution, high CPU capabilities, right? So you want sort of, this goes up, right? If you have more resolution here, this goes up, which means that this goes up. Your battery or something to charge goes up, right? Which means that this goes up, right? The network kind of goes up, right? And the dollar for all of this goes up, right? You don't want to worry about the dollar cost right now because this is still some emerging kind of technology. But all these things go up, and what they're trying to do is figure out what is reasonable for what we have right now, right? So if it turns out that if you want to have high, HD TV resolutions, if that meant that you need to have a rack of servers, that's not feasible right now, right? You don't want to set up a rack up there. So as long as you can have some, some small, something which can be powered by the battery, then you want to go with what that is, right? And it's incredibly interesting that the technology keeps improving. So for their project, they used Xscale processor, which is popular in many PDAs and stuff. So in my lab, we had wire-based systems. We did that a couple of years back, wire-based systems which are a little bit bigger than this ones, but it can do a little bit more processing, compared to these ones. They can do a few frames per second, not necessarily 30 frames per second or something, right? And they didn't have enough memory to even do larger frames, right? Because there are issues of getting the stuff off the camera and stuff like that. One of the other components you want to have is some sort of a storage. Because what happens is, if you don't have storage, everything you capture has to be sent somewhere else for processing, or you have to do the processing yourself, right? And if you couldn't do the processing right away, then you have to throw it because you don't have local storage, right? The other thing you would like in these systems is, if you didn't know what questions to ask, you would like to sort of go back and ask it later, right? So if you look at the data and it looks like you're seeing something that you didn't expect to happen, you would like to sort of go back and say, I'm seeing this, but why did it happen, right? So I would like to go back in the past. And one way to do that is to send every image to the central server and then go back and forth in history. But in this kind of setup, you can't, because if you have 1,200 of these, having the aggregate, so if you have 1,200 cameras, right? And if you have one server setup where all these are coming, right? Now you're seeing massive amounts of data coming in. You might be able to deal with all this stuff, right? So those are the sort of the big issues that you have to wrestle with. One is the cost, but at this point, let's not worry too much about the cost. And you need to worry about what sort of a camera you want to have, what sort of all these things, right? So that's at the high level, right? The next step you have to worry about is how to actually deploy these things, because you want these to be out in the field, right? So you have to make them weatherproof. You have to make them stand up to the elements, because like I think the camera people pointed out, you have to sort of know how much wind, how much rain all these things get, because you don't want to constantly go in there and repair this. You would like to deploy them and not have to go back maybe for a year or years at a time, right? That adds lots of tricky problems to these set of systems that you don't really think about. I think I mentioned once, London has lots of these cameras monitoring the people down below, right? And the London ones are not wireless. I mean, these are essentially cameras which hook up to some central site where they can monitor the cameras. So all these cameras are so you have a camera here hooked up using very good connectivity to some backside where it's stored or what have you, right? And one of the problems they found out was, the resolution was not good enough. I think it was VGA style, which is not good enough it was good enough to know that there was somebody there, right? Which is not that useful, right? So if you see a bomb explode and you saw that there was one person who walked up and planted the bomb, that's not terribly useful, because you kind of expect that if that even happens, somebody must have done that. You really want to know who it was, and you need a resolution to keep up with that. But more importantly, these things tend to get dirty and gunky, right? Because all of them are pointing out through one lens, right? The quality of that thing keeps going down depending on either because there's some moisture condensation or the dirt forming and those things. So you would have to keep them cleaned up all the time, right? And it turns out in the London system or in any of these systems, you don't have the operational budget to have one person with a little squeegee going around cleaning those cameras, right? So I don't remember how much cameras London has, but I think it's a lot, right? Let's say you have 20,000 cameras, right? So you need to have a bunch of users whose job is to go around and clean these cameras day in, day out, 8-hour day, just go and clean these things, right? That's not really feasible, right? You don't want to do that. But turns out there's not a whole lot control you have as a computer scientist, because you're out in the nature, so things like this happen. So you need to develop the new technologies to fix these things, right? So for example, in the case of the Oregon coast, right? So when you leave these things, naturally it gets really messed up because you have the rain and salt water coming into those things. So you need to have some sort of thing to wipe this off, right? The other thing is to charge these things. You need some sort of way to charge these things. Clearly batteries aren't enough, because now you have a lot more computing, a lot more all this stuff. So think of this as your cell phone, right? So your cell phone has sort of your camera, sort of your little bit CPU, sort of a little bit more network. Your cell phone lasts for a couple of hours, right, before it runs out. Especially if you keep the camera on all the time, it lasts for like an hour or so, right? And that's clearly not acceptable. So you need to figure out how to charge them and recharge them, right? So how would you charge these things in a coastal setup? What sort of a thing you can think of to charge these things? These are by the Pacific coast, right? So there's constant wind, right? So you can think of putting a little windmill, right? Little windmill to get enough energy, right? I mean, it's not that much, right? So do you think that you could do that?
I don't remember ever hearing of a small scale windmill, but I don't know.
They said they could build some small enough scale to get, I mean, you're not trying to get lots of energy, right? You just want enough energy to charge these things. And given sufficiently strong wind, you ought to be able to run these things, right? Because there's not much of a concern with the aesthetics, because you're not trying to build a big thing, right? So let's assume that you can build something small, right? So obviously it can't be like this small. Maybe let's say this big, right? So if I build something like this big, which gives me enough energy for all I want, and the nice thing is, all these cameras can be shut off at night, because nothing happens, so they can charge overnight and then basically use the stuff during the daytime, right? So you could do that, except now you have to figure out how to align the blades, right? You can either put the blades like this, where you get a lot of wind, like if it's spinning like this, and turns out birds fly right into it, right? So you don't really want to do an experiment where you're a killing field of 1,200 things killing the birds, right? So you don't want that, right? Though technically it works. I mean, you get your energy, but you are constantly killing birds. So you need to figure out how to put these things where you don't kill the birds, right? Because the whole study is it's out in the environment, and it's not nice to say you constantly kill birds, right? So now you need to figure out how to hide these things, right? The other alternative is to have solar panels. I mean, you basically solar panels all over the place on the roads and everything, right? So do you think that will work here? The first thing is, of course, Oregon is not exactly sunny many times, and it's cloudy and stuff, but other times, would it work? Turns out the birds either commit suicide or they poop all over the place, right? So, to have solar panel, you have to have a panel which is kind of pointing up like this, right? You can't have it like a thin blade. So you have a thing like this, and if you go to any of the beaches where they have these, some of the beaches, even by Lake Michigan, they have these things, right? They have a little panel up there, and you notice all the birds now love this place because you have like this coastline with nothing. No trees and stuff. Now suddenly you have this thing sticking out with the solar panel, and so they start to live there, right? I mean, they hang out there all the time, and they do what they do. So somebody has to go up and clean these things, and again that defeats the process, right? So a lot of the things that you sort of know could work can't really work because of these issues, right? I mean, the birds are a major annoyance, right? And essentially, because it's by the ocean, if you go to any beach, you see all the seagulls and everything, right? Essentially, you're creating these things, and you can't solve some of these problems because the camera has to kind of stick out, right? So if you're monitoring temperature, I can kind of hide it underground somewhere, or hide it in something. But if you're monitoring these sea phenomena, using a video camera, you want the camera to sort of look, stand out and look. So once it stands out and look, then it's a place for birds to sit and everything, right? So there are other issues that you may or may not be able to solve, and that calls for different kinds of solutions. And then once you get past those, you still have to worry about these challenges. You don't worry too much about the cost, because since you have to kind of set these things up and leave them over there, the cost of deploying them is sufficiently high that the cost of the equipment itself is not the worry, right? So in the case of the glacier thing you saw, right, they're basically flying from somewhere to go all the way. So if you say after you fly over there, the camera is going to cost you like $5,000, you don't particularly care, because the flight up to that point is probably like $50,000 or something. So you don't really care about that little cost, right? So that's sort of things that people are facing, but the interesting stuff is people can see what can be done with these things, right? So once you have this ubiquitous kind of monitoring of whatever events, using as high resolution as possible, and the interesting part is all these things are now feasible for you to do. I mean, you can buy CPUs which are capable of doing this stuff. If you can solve these, how to power them, then you can go beyond these things, and you can start thinking about different stuff, right? So this is good for environmental monitoring, right? What about monitoring people? What about, let's say we want to have a couple of cameras here monitoring this classroom for what have you, right? We'll solve a lot of the other problems, right? I mean, there's no birds here. We can probably power it with the power supply from the campus and stuff. What do you think of such a system? we can catch the next 9/11, right? That's the premise of these systems, right? Yeah.
Well, you're going to be generating an awful lot of data, so you have to first of all store it and then analyze it somehow. It's going to take probably a lot of people to go through it all and stuff.
Yeah, so you need to have develop automated stuff, right? And once I throw the buzzword, this is to prevent the next 9/11, right?
Yeah.
What is money compared to that, right? I mean, within limits, right? But what does it mean for privacy, right? I mean, all these things I haven't talked about that at all is privacy and those concerns, right? So one of the reasons why they picked stuff like this is the waves are okay. I mean, waves don't care if you take pictures every second or so. But when it moves to the human being stuff, then you have some concerns, right? You have some concerns. You want to worry about the stuff, right? Incidentally, we are monitoring a lot of spaces within Notre Dame, right? You probably noticed those cameras, right? Alexander is not here, but he says like they put all the cameras from the quads, the pictures from the quad online somewhere within Notre Dame. So he wrote a program, I think a year and a half back, which basically FTP said file over, right? And just collected all the images, right? So for the project one, he actually collected a video of all the pictures, right? Unfortunately, he's not here, and I haven't seen the video of how he created the stuff, right? So, we're not doing the sort of the things that all the high tech kind of stuff, but essentially there's some cameras watching over the stuff, and it's putting up the pictures online somewhere. I don't know if Notre Dame is actually storing those images somewhere, but it was very trivial to write a script which will just download the pictures. So you have the picture of the last year, right? So that brings up the issue of we don't know if any of us were in that images and what we did and all those things, right? And we haven't really had to deal with those things. We haven't really had to deal with the privacy and those aspects of video sensing, because we're trying to look at the goodness which comes out of it, which is trying to find the bad people. But by definition, if you want to find the bad people, good people happen to be inside the system, and how do you make them be aware of both of those is one concern that we haven't had to deal with, especially if you're doing something like nature and stuff. But the logical conclusion is towards a point where we can censor things, right? So this is one project. We'll see another project which came out of UMass Amherst, and there are a few people who are working on stuff like this, because essentially, since we can do these things. So essentially, this particular board it's very similar to your PDA. It's a scale processor. It's basically a PDA, and it has your PCMCA card. It's a few years old, so it has the wireless card to it, and they got a USB camera. The same webcams you can buy off the shelf. So this is probably like a couple of $100 at best. I mean, these are not exactly pretty high tech. I got virtual. There's a company called Virtual Cog. They make these little kind of Lego kind of computing. You can kind of connect these things to make a bigger computing. So that one is like fairly small. Comes with a video camera that we have. I haven't used it. I'll try to bring it on Friday. We can take a look at it to see what we can be done with that. So you want to deploy lots of them. So you want to deploy as much as possible, as freely as possible. There are a lot of issues with these things which we haven't talked about here. One is, if I want to measure the temperature, average temperature of this room, right? I can put some sensor throughout this room. It doesn't matter where they're looking, because you kind of look at what you're trying to do, right? But for video sensing, it has to look at the right place, because you can't just throw something here, right? I can't put a camera here. I have to sort of lift it up here to know where it's looking. So if you want to do correlation between 2 or 3 cameras, you have to sort of make sure that they are all watching the right spot, right? Because if one is upside down or something, then you want to know what all these things are seeing, right? And that's very tricky even for manually setting up these things. So if you're setting this up using a human being, you still have to go through a lot of stuff to figure out where exactly it's pointing, what it's seeing, and all those things. But what you really want is, I give you 10 of these and say, deploy them in the classroom. I want to know what's going on in the classroom, right? And that's being able to figure out where you are watching, so I can know what is being watched. That both of them are not watching two different things, but the same thing, and we'll see more of that in the next system. So you bring a lot of these issues, and essentially you're taking whatever we talked about media servers on steroids, right? As many of them as possible, except on as low computing as possible, as cheap of them as possible, right? So in this particular case, they used PCMCA. They used USB 1.1 because that was cheap at that point. And USB 1.1, then you realize all the limitations of USB versus FireWire, right? FireWire, essentially, these two are peers. So the computing for capturing the image is on the FireWire card. For USB, your CPU has to do all the stuff. So your CPU now has to capture these images, half the thing. They couldn't do video. They had to do multiple images, try to do processing later on. And the issue of what to process, right? So I want something. So if this one knows something, it sees like red object or something, I want that information to come to me, right? I want this information to come along this path, so they know more and more information about what was seen. So maybe at this point, this and this can correlate, and then say I saw a red object. So these two saw a red object kind of stuff. Whereas the real image is here. So you get some image saying somebody saw a red object on 3 of these camera views, and then you can send back a query back saying I want a better, what exactly is that object. So you can do this processing. So essentially, your video object, your image tends to live here and live halfway along, throughout the system. So how do you send annotated information about what you saw without the whole thing? How do you manage these little chunks is a big challenge that they were trying to address. And how do you program these things to change this stuff? So you don't want them to be static. They used a Python-based platform, which is what the particular talk was talking about. And how do you, so you really want to say, did you see the red one? So, now try to see what it was, right? So I need to program these things on the fly. And all these things have been people done for sensor networking scenarios, but now you're talking about objects which can take as much computing as you can throw at them, and how do you proceed with that, right? So we are sort of out of time, and I'll continue with this on Wednesday.